That's an auspicious day. Uh, you are not in the Zoom. Ah,
All right, I'm there now. That's good.
yes. You check to see if your audio is connected to
Yeah.
the mic.
Oh, what? Okay.
Check the audio setting.
Oh, yeah.
Yeah, it's not.
I didn't know whatever shows up.
Not there. Yeah.
Well, that's fine. They can hear me through the speaker. Do you have announcements? Oh, yeah. Okay. I wanted to have background music for you. Oh, well, next time. What's announcements do you have in mind?
You also have the like calendar up.
Uh, sure. Okay.
All right,
Go.
the
Sorry, not my calendar.
Good afternoon. How's everyone doing? All
Later.
right. There's still people filing in. If you're sitting next to an NTC, can I ask you that you move inwards towards the center? Just so that the NPCs are closer to the aisles. There's a few seats over here. If you move inwards a bit.
All right. What else we got?
Other than
Timing's
that,
tight today. Yeah.
Uh, Happy New Year, everyone.
Ooh.
Woo. Yeah. Other than that, I think what's homework 0B is due to?
Yeah.
Yeah.
Today.
Homework 0B is due today. Make sure you finish that. Other than that, mini project, the 2048 project is going to be due, I think, next Tuesday or Monday. Next Monday.
Yeah.
Next Monday.
All right.
So those are the two major assignments. Make sure you get working on that.
Great. Thank you. All right. Other quick announcement. My office. What's that? Oh, I'm not. Thank you. My other quick announcement is that my office hours start next week. They're on the screen and they'll be on the website shortly. Come talk about anything. Doesn't have to just be 61B. All right. Let's get going. Let's talk about lists. So today's goal is we are going to make a more industrial strength list. We won't quite get there by the end of the hour, but we're going to make int lists better. That's the goal. And so we're going to start by telling you something you may not know. So in the somewhere early in the Abrahamic religion Bible, they have the story of Adam and Eve who eat from the fruit of knowledge and realize that they are naked. So I'm here to tell you that's what happened to you. You're not literally naked. This isn't that dream where you're in lecture naked. But the int list is a what I call naked recursive data structure. It's an awkward data structure. It's hard to use, and we're going to try and make it better. That's our goal. Let me give you a sense of why it is an awkward data structure to work with. Whenever somebody wants to add something to the front of an int list, this beautiful thing we constructed, they have to be thinking about references. This is just weird code. people would be upset if this is how they had to write code. So the whole point of today is we're going to make it better than this. We're going to hide this nakedness so that the list is useful. So I'm going to do a number of improvements. Today's just improvement after improvement after improvement. And the first one we're going to do is we're going to rename the int list class to int node. And then I'm going to delete everything, pretty much. Not everything, literally, but most everything. Okay, so all this can go. All this hard work we did last lecture, it's gone. And now we're going to rename a couple of things. Instead of first, I'm going to call this item. Instead of rest, I'm going to call this next. So item and next. And that is our first improvement. Okay, so that might seem a little silly. Like, who cares? All you did was rebrand everything, but that's exactly true. And we're going to make things yet nicer. Okay, so that's our first thing we've done. We just took int list and we deleted everything we did last lecture, except for the variable declarations. Okay, and that's because we're going to be isolating, ultimately, this recursive data structure from the end user. We're going to silo it away because it is strange and hard to think about. That's our goal. Okay, so the int node class is the int list class with no methods and with slightly different names. Okay, the next thing we're going to do is we're going to create another class called SLLists. Okay, we'll tell you what SLList means much later, not even today. But I'm going to make a new class. All right, that whole thing. All right, sorry. I don't know why. Whenever we're in here, there's this laggy thing that happens, but that's okay. So I'm going to make a new class, and I'm going to call it SLList. Ignore the dog here. Not important. So here's the SLList class. And what is an SLList? Well, an SLList is going to be a list of numbers. Okay. What does an SLList have in it? Well, it's going to have, first of all, it's going to have an int node, which I'll call first, and that's going to be the first item in the list. And it's going to seem super weird that I'm doing this. Like, it just seems insane that all I'm doing is like just moving stuff around. So it'll all be okay. And then in my main method, well, actually not yet, it's also going to have a constructor, which is going to take an integer, and it's going to say first equals new int node with x and null. Then in the main method, when I instantiate an SLList, I'll say SLList L equals new SLList, let's say 15. Okay. And that's the SLList class. So I basically added a level of bureaucracy. So far, the two things I've done are one, rebranding, and two, adding this layer of bureaucracy so that if I want to create an SLList, the only thing I need to tell it is the number 10. Whereas this naked recursive int list, you can see it's a little more awkward because I had to say, you are an int list, your number is 10, and your next is null. So already the SLList maybe feels a little nicer because it's easier to instantiate, but we'll see there's some more advantages to come. Okay, let's just a little more before I take any questions. All right. So we're going to add an add first method. That's going to be our next little trick. Every time we come back to this window, though, I have to click somewhere and then click again. I'm going to add an add first method. So it's going to be public void add first. And I have a particular integer I want to add in mind. And the way I'm going to add a new number to the front of my SLList is I'm very lazy. And I'm going to go back to the previous lecture's code and think about how we added numbers to the beginning of an int list. Here's an example. What does this line of code do? Adds 10 to the front. So we're going to mimic that with an SLList. And we're going to say, if I want to add to the front of the list, I'll say the first item in the list isn't what it used to be. Now it's X. And then whatever used to be that was at the front of the list, it's going to be the rest of the list. That's going to be the goal. And this shouldn't say int list. It should say int node. There we go. And this should not be imported. All right. So that's what the add first method looks like. We add numbers to the front of the list. And now if we do l.add first 10 and l.add first 5, we are going to get something nicer. So let me run this code here. So after running this code, we look in the visualizer. After we've run 15 and 10, we have a list with 10 and 15 in it. When I click this line, I expect 5 to appear as the front item in the list. And indeed it does. This is good. And I'll take a couple questions shortly. Not by now. The last thing I want to do is write a get first method for now. How do we get the first number in the list? If we want to get back this 5, just looking at it visually, how do I get this? I ask for first dot item. So when I ask for first, that gives me this memory box. We follow that pointer, and then we ask for the item. So we'll just say return first.item. And so indeed, if I go here, and I say, I need a little more room here, sorry. If I say system.out.println l.getFirst, then I get back, hopefully, the number 5, and we see 5 got printed. All right, good. Okay, so let's reflect on all these steps that I just whipped through really quickly. This add first and get first method, the difference between what we're doing before and what we're doing now is that this SList is really easy to use. Even if you didn't digest every step of that high-speed coding process, when I created this SList, I just said, SList, I breathe life into you. You are the number 15. You have 10 at the front now. You have 5 at the front now. Now I can get the first item. It feels very comfortable to use, unlike the more awkward int list. All right. So let me compare these two. And this one I'll take questions. If we compare these two approaches, the previous lecture where we were working with recursion directly on the right, we had to create int lists. And if I were a user writing like a spreadsheet program or whatever it may be, the way I'd write my code would be to write each of these lines of code, thinking about the recursion as I go, which is just awkward. By contrast, an SList hides all those details. It has functions where you put numbers in. It has a function where you get a number out. You don't need to think about references at all. So SLists are just much simpler to use. You just use the methods. You don't need to be thinking about pointers, references, whatever you want to call them. Now you might say, why don't I just add an add first method to the int list class? And it turns out if you were to try, there's just no efficient way to do it. It's not possible. You can try if you want. You'll see it's hard, beyond the scope of what we want to do in lecture. Right, we're setting up an abstraction barrier. Here's another way of looking at it visually, which is that with an int list, we don't have these abstraction barriers. The user of an int list is pointing directly at the nodes. They're naked, they're dangerous, they're radioactive, they're tricky to use. Whereas the user of an SList, remember your users could be middle school students learning to program for the first time, people who are, very sleepy. This is just easier to think about. It's easier to reason about if you're using this kind of list. So with this other approach, the SList approach, there's this middleman, this intermediary that you have to go through, right? So L1, we go to this node, and then it has its own hidden first variable that you aren't really thinking about, and it points at the naked recursive list under the hood, and the user asks using the add first and get first methods to add information or to retrieve it from the list, right? So this is the maybe the more, I don't know, Roman Catholic approach. You have a priest that is an interceder between you and God. This is the more Protestant approach. You go straight to God. I'm not an expert on Catholicism or Protestantism, but I think what I said is correct. All right, questions? Yeah. Yeah, the actual code? Yeah. Okay, sorry, we got to do the magic quick. Line 15. Yeah. Well, that's a blank, so. 13, yeah. It is the same as saying this dot first. That's the same exact. Int node. Constructor for int node. They are the same. Still on line 13. Yeah, if I do this. Oh, this one right here? Yeah, also the same. Yeah, no effect. Other questions? Yeah, onto the slide. This one or next? Next. Okay. It's a subtle difference. It took me a long time to understand this when I first learned. Yeah, sorry.
If you wanted to force the user to have to go through your defined methods to modify first, then in the class for SLLists, should you change public to private?
You knew exactly where I was going. Perfect. Great. So one of the issues with the code we've written is that the priest's barrier between us and God is not firm, right? We can go around the priest. In particular, let's suppose I have this SList. It is possible with our code to say l.first.next and manipulate the pointers directly or the references and then say that, well, l.first.next is going to be set equal to l.first.next. In other words, if you think about it, you're doing this. Like if you run this last line of code, you're making an invalid list that we can think of as, I guess, the number 10 followed by an infinite number of 15s. But that's not something we want to be possible. We want to hide the details. Like we want to make the abstraction barrier even firmer. Okay, so let's hop over to the code real quick. And I'm going to give you an example here where I'm going to say, okay, click. I'm going to imagine that I'm going to call this SList user. This is you're imagining that you are programmer using the SList class. You say I'm going to copy it from the SList class from the main. Let's get rid of this main function. Okay, this is somebody else, whoever they might be, writing any program. That's all fine. But what I don't like is that I can say L dot first equals null or whatever. Like that's nasty behavior. Okay, we don't like that. So we're going to go into the SList class, and I'm going to change this to be private. This is a feature of the Java programming language, which is interesting that all it does is make programs compile that would otherwise compile. And the reason we do that is we're creating a firmer abstraction barrier. Unlike in Python, where you can add little underscores to kind of signal to somebody, like you shouldn't mess with this, with private, we really mean it, and the compiler will enforce it. If I put my mouse over this, it says first has private access, and you can't access it from this class. Okay, so that's private access. Okay. So if you ever wonder what public means, it means anybody is welcome to use this. Private means only this class itself can manipulate this object. Yeah.
If we go to compare private or public, what's the deal?
If you don't do public or private, it's something else called package protected that I won't teach you. It's just a software engineering thing that's not important enough. But you can read all about it. Okay. So this private keyword makes it so the compiler won't compile code that breaks the abstraction barrier that you've specified. So why should you do this? Well, one of the reasons is you're hiding details from the user. They never need to know that there's a first pointer. If they're using IntelliJ and they're like tab completing, it won't show up on the list. Another reason, so that's important because it's just less that people need to understand. Because if someone doesn't even know it's there, they can't use it. The other thing that's really nice is you can change it if you want. So maybe you decide you don't want to call it first anymore. You want to call it friend or whatever. And you can do that because no one's code could possibly be referencing first because you made it private. So if you have a private variable or a private method, it's something no one else can use, and you can reliably change it in the future. An analogy would be, for example, in a car, you have a public interface, right? Sometimes, like all cars, I think, have pedals that change your speed and a steering wheel that steers you. But they don't all have underneath the hood a fuel line. Electric cars, there is no fuel line. And there's like a layer of interface between you pushing the gas pedal, or the accelerator, I guess I should call it, and the process under the hood that makes the car speed up. Okay, so public is what everybody knows, private's what you keep to yourself. Now, despite this term access control for these type of modifiers, it has nothing to do with like keeping your code safe. It just means other programmers who are working on your code base, they can't mess with those details of the class. Any questions about this? Okay. All right. Nested class. So there's just another little syntax improvement I'm going to make, which is I don't really like that the int node class is its own separate class. So Java does allow you to nest classes inside of others. So I'm just going to take the int node class and I'm going to pick it up and I'm going to pull it out of this file completely. And I'm going to put it in SList. Okay. And then once I delete int node, because I don't need it anymore, this code will work just fine. So all I did is I moved int node inside of SList. And the reason I did that is there's no reason that anybody needs to know that int nodes exist. They're actually they're a detail that's part of the SList class. Actually, a slightly better way of putting it. Int nodes don't need to exist outside of the SList class. They're just like a building block for SList that no one's going to use for any other purpose. That's what I've decided, at least. Okay. I can also make this class private, which means that nobody else can make int nodes, which again makes sense to me because how would you even get one? The only thing I could do so far is add first and get first. There's no way to there's no reason to think about int nodes. So I may as well make it private. Okay. I'll note that often the convention is that you put your nested classes at the top and then your instance variables and then constructors and then methods, but you may work somewhere else where they do something else. And it's up to you what convention you want to use. Yeah.
private class has a public variable that works.
Right. If a private class has public variables, it turns out that once you declare a class as private, these excess modifiers no longer matter. So you can delete them all if you want. But it's one of those like Java details that I don't find that exciting, but you might. But yeah, these don't actually matter once I make it private. Interesting thought. Yeah. So what I think about nested classes, they're useful when a class doesn't really stand on its own. Like when it's obviously subordinate to another class, it only exists for another class's use, then make it nested. And if none of the methods ever expose one of those objects, if you never have a return node method, you may as well make the class private. It doesn't hurt to leave it public, I guess. But to me, just the clean design of Java, the more constraints you can make, the better, so that people don't try to do weird stuff that might bite them someday. Okay. So the way I think about it, it's hard to imagine some other class needing to ever work with an int node. But if we wanted to, we could, in theory, return a get front node method. If that happened, then we should make the int node class public, right? But private makes more sense. Questions about this? Okay. This is an annoying slide. I apologize for even telling you about this. But static is something, you can also use static in this context. Let me go to the code and give it by example. Does this int node class use any of the SLists instance variables or functions? No. I could like print out the first. That'd be a weird thing to do. Anytime you make a node, print out first. And that would print out the entire list's first item every time you make a new node. But we don't like, there's no reason to be using first or add last or anything in here. So if I change this to be static, the node class loses the connection to its enclosing instance. I mean, I really don't want you to, like, if you're pretty comfortable with programming and you understood what I said, great. If you didn't get that, this is so not important. But I figured I'd mention it just in case. For those of you who are pretty strong programmers, the reason you might do this is it makes each int node slightly smaller in how much memory it takes because it doesn't need to remember what list it belongs to. But this is a minor detail that's not super important to us. The basic idea, though, is that if your inner class, your nested class, does not use any of the outer class's stuff, then you may as well make it static. But this is not a Java class, but I felt like I had to mention it. Yeah.
Can you still make of that class?
You can still make instances of int nodes even if it's static. That's fine. It just means this class doesn't know about its enclosing class's members. But again, I apologize for even telling you about it. Okay. All right. Let's do something a little more interesting, which is I want to jazz up my SList class a little and add some more capabilities. What I'm going to do, so actually, just to summarize what we've done so far. We had our int list last time, which hopefully felt somewhat comfortable. Now we've rebranded, done some bureaucracy, changed the class from the first node from public to private, and then we brought the int node class inside. Those are the things we've done so far. What we're going to do next is we're going to write an add last and a size method. I have in the lecture code repository. If you guys want to look at it, if you're watching this on the webcast, you can try and write this code, but I'm going to do it here in person because I can't freeze time and have you think about it. But it would be cool. Okay. Let's go into the SList class and let's add ourselves an add last method. So the add last method, we have a specific integers that we want to add to the list. And this one I'm going to write iteratively. I could write it recursively, but I'm going to do it iteratively. And I'm going to start by creating a pointer p, which is at the first. And then I'm going to say advance p until it is the last item. Okay. How do I do that? Well, I'll say while p dot next is not null. What do you guys think? P what? P equals p dot next, right? Once that's done, what I have in my mind is p is pointing at the last item. If p is the last item, how do I add the number x? I say what? P equals something. What do you guys think? P dot next equals something. A new int node, construct an item, yeah. And what goes in that node? X and null. This is going to be pointing off the end of the list. Okay, that's add last. So we go into use SList or SList user. If I add 20 at the end, I'll add a little breakpoint here. We'll run this code. Hopefully it runs, it's not going to run the right one because it says SList. Hold on a sec. I want to run you. I want to run you. Why can't I run you? Oh, something already running? Uh-oh. I don't like that. Why is it grayed out? Okay. There we go. All right. Okay, here's SList user. Here's the state of the list before we added last. We step in. I'm going to run to this line of code. We expect P to be pointing at what? The last item. It is. Look, P is pointing at 15. Great. And then we're going to say P.next equals new int node and visualizer. There you go. Now shows 5, 10, 15, 20. Now I should note, you guys have not had a lot of practice with this kind of list manipulation. So if this feels very fast, do not fret. You're going to spend tons of time writing this kind of list code pretty soon. Okay. So that's the add last method. Any questions about add last? Yeah. You could not make it a new SList. That wouldn't make sense. Yeah. Because SLists, they don't have a second parameter.
Okay, but doesn't it like default?
If you did that, it wouldn't work because in this case, an SList is what you're creating, but it wants P.next to be an int node. So they're two different types. Int nodes are just the nodes inside, the radioactive godlike material. SList is the
It's not like it's no.
int list dot first.
Like S list dot first, then that.
I don't know. I can't parse it well enough. So I'm going to save that one. Other questions? Okay. So let's fix it again. So that's add last. Let's talk about size. So I'm going to write a method that returns the size of the list. And again, we're going to try and do that recursive thing this time. I'll notice an interesting pattern here, which is you want to do like if some case, return 0, otherwise return like 1 plus next dot size. Like that feels tempting, but the problem is there is no next, right? Because I'm not a node. I'm the entire list. You're asking the priest to like recurse on himself, but he's just a guy. Okay. So the usual way, there's a few fixes for this, but the usual way, and I'm just going to give this away as a design pattern for these kind of intermediary classes that have naked recursion inside of them, is I'm going to create a private int size method that takes a specific node. And here's the important part. I'm going to write a comment up here. This function returns the size of the naked recursive list. We don't need that space. Starting at node P. Okay, that's what it's going to do. How do I do that? Well, we actually did that in the previous lecture. This is the one where we say something like if P is 0, or sorry, null, and we return 0. Otherwise, we return 1 plus, what do you think? Size of something. P.next, right? So this is the naked recursion in action, right? We're manipulating int nodes. They have a next. Okay, so the difference was the priest, the intercession, the guy who's interceding on your behalf, he does not have a recursive next person. So we have this little helper function here. Okay, this takes a while to wrap your head around, but here's the part that's pretty interesting, okay? So if you trust that this method works, how do you get the size of the entire list? Return the size of something. Someone maybe on the backish. Return the size of, here you go, this cluster. What do you think? First, great, I love it. So that returns the size of the list starting at the front, which will be the entire list. Okay. So if I do if I say print out the size of the list, we hopefully will get 4. And indeed we do. Good. Okay. Let's look at this on the slides though. It's quite a lot to digest here. Okay. So what we just did, this is a very common design pattern again, which is I have a non-recursive class that is working with other recursive objects. So what I'll typically do is I'll create a private method that takes as a variable, like one of those naked recursive objects, and then I'll just ask for this function called on whichever one is notable. In this case, it's the first one. Yeah.
So obviously the private, but is the bottom one.
Is this function recursive? I would call it not. I mean, I don't know. This is semantics. I would call it not recursive on itself.
Second, the size that you're referring to the one above.
Right. This size right here is referring to this top function. So in Java, we have multiple functions with the same name. The way that the function dispatching works is that it knows I need to call the one that has one parameter. And then this one's going to recurse on itself. Yeah. Okay. All right. Okay, any other questions about this? It's a cool pattern. Feels nice. All right. Question for you to ponder, which is how efficient is this size method? So let's say that size takes 2 seconds on a list that's 1,000 items long. How long do you think it'll take on a list of 1,000,000 items? Here's a little question that you can answer. It's the only one to... Yell at me, not letting you answer. I think it should.
Yeah. But what do you do? Yeah.
All right, so many of you observed that it is pretty slow. The exact correct answer is 2,000 seconds because it needs to spend 1,000 times as long literally going through the list. And this is very slow. So the next thing we're going to do is make size better. So I taught you a cool pattern. You want to recurse on recursive data structure, you can create this private helper method like this. I'm going to show you an even better pattern for this one, which will be a little disappointing after all that, which is I want to make this very fast. In fact, I want to do it like in constant time. So what I'm going to do is I'm actually going to create another variable here called size. Then when I create the list, what should the size be when I first start? 1. Okay, when I add an item, what should I do? Add 1. I use plus equals, sorry. You can use plus plus if you want. Size plus equals 1. And then what should the size method do? Return size. Now, unlike Python, where you can't have variables and functions with the same name, in Java, it's fine. Okay, so I just deleted all this stuff. Okay, we spent all this time like, oh, all this weird recursion stuff. Sorry, we got rid of it. And now when we run our code, it'll give me 4. And now it'll be really fast. Okay, so there it is. There's my 4. Okay. Now I showed you that pattern because you will use that pattern of the private helper throughout project 1 later. Okay. All right. So what we did here is we made a special size variable that caches the size of the list. This is like memoization if you took 61A. We're putting aside this data to speed up retrieval, but there's this old saying that there ain't no such thing as a free lunch. Here's some random image that I grabbed from the internet. Because you are actually spending effort to keep that size variable. Now, every time you call add, you have to add a number, which will actually slow your add method slightly. But I would say that overall, it's a net win. Every add call takes slightly longer, but the size methods are fast. I think it's, I mean, that's the trade-off is bad. All right. So let's reflect on what we've got so far. Our old naked recursive list that is hard to work with. It's a strange object. But here, with this middleman, we can start not just hiding the naked recursion, but we can start using this middleman to do bookkeeping. I can keep a size variable around in addition to this first variable. It lets us store this meta information to be very fast that we can maintain over time. It's a very big deal. It's a subtle little difference in terms of object-oriented programming, but it is, I mean, kind of amazing. Any questions about that? Yeah.
What's the point of like a linked list structure?
What's the point of even doing a linked list? Well, unlike an array, which is our only basic thing we have in Java. So what we're trying to do is build lists out of nothing. And arrays, they have a fixed length. So what I've just showed now is a way that we can build an infinitely extensible array. So we will cover array lists, and it'll be an interesting trick. That's in like 3 lectures. Yeah. Well, everything we've done so far, there's nothing the only native data type we're using is int. Yeah. So we made our own list from scratch. Yeah. It can't do all the things lists can do yet, but we're getting close. Other questions? If any, give you a chance to reflect. Okay. So one meta point I want to make here is that the specific lines of code I'm writing today are not as important as understanding this diagram. That's what you really want to be getting out of today. Understanding the exact lines of code kind of comes with when you do the homework. All right. Let's talk about something else we can do now that we've added the size variable, which is that we're going to be able to make our lists empty if we want. We'll be able to capture the idea of an empty list, which we couldn't do with int lists, not very naturally at least. They just have to be null. Before I do that, let me summarize what we've achieved by having an SList class so far. One thing is our size method is much faster than it would have been convenient to do for an int list. With an int list, there's no special place to store that size variable that's common to all of these nodes. There's nothing that they all share. At least in Java, there's no easy way to do that. The user of an SList doesn't need to know about the naked recursion. It's easier to use. The add first method is more efficient. And if you want, you can try and write one for int lists and you'll see it's slow. And then it also allows us to avoid errors or deliberately bad behavior by making things private. So there's a lot of little changes that having an SList, so a lot of little benefits that the SList idea gives us. So the next one is let's represent the empty list. So, oh yeah, please go ahead. Right, getters and setters, yeah. You can think of it as a getter, but it's not quite the same thing. I'll talk about getters at a future date when it's more natural. Because in APCS, you don't jump straight into data structure. So at some future date, I'll tell you what a setter is and getter is more specifically. So if I want to make the empty list, what am I missing? Like, what do I need to create? Like, if I want to represent the idea of an empty list, what do you think I should write next? I need a constructor, maybe that represents an empty list. What's an empty list's size? 0. And what's first going to be? Null. Seems fine. Great. That's an empty list. And if I do that, and I go to SList user, I'm going to delete this. If I run this code, I don't want to delete the whole thing. I just want to delete the number. If I do that, I start with an empty list, and then I add 10, then 5, then 20, and then we get back that there's 3 items. I guess I'll pause this, or actually I'll do a little visualization showing you that before this line of code runs, there's nothing. Then we have L, which points at an empty node. This is an empty list. Then I can add first. So we were able to capture this idea of an empty list, which is not very natural with int lists. Now there's one bug here that is really annoying, which is that if, oh gosh, I'm gonna do that again. All right. If I were to delete these 2 lines of code and I try and add to an empty list, my code will crash. Okay. Cannot read field next because P is null. I'm going to click this. This is good practice for you. I'm going to click here. That's the line of code it's crashing on. I'll run it again. Okay. When I get to this line of code and I'm trying to add that first number, the number 20, it crashes here. And why is it crashing? Well, you're asking for nulls next, but null doesn't have a next. It's not a thing. So I guess a question for you to ponder for a second is how would we fix add last so that if the list is empty, right? Let me show you what the empty list looks like real quick. Actually, this is the empty list. First is null. How do we change add last so that we don't have this problem? Add a condition. Okay. So what would be that condition? Somewhere in this general quadrant. If the list is empty, do something special. Great. All right. So let's try that out. If the list is empty, oh boy. I'm so sorry about the slightly annoying user stuff or user interface stuff here. All right. So we're going to have a special case, which is that if first is null, then what should I do? Well, I'll say that first equals, almost, new int node x null. And then I'll return because I don't need to do anything else. So if first is null, do the special case of creating a first node. And that will fix the problem. If I run it, I get back a size of 1. Or alternately, if you'd like, I can use the debugger and we can show that if we call add last, it behaves itself now. We had a special case that if it's null, then say that first is a new node, like a hard-coded special case. Okay? And that's fine in this case, but there's other ways that are better. So this will work. I mean, it's fine. It will, and some of you may do this when you do project 1A, but I want to convince you of a better way to do things. Before I do it though, any questions about that? Yeah. Yes, so sure. I think that's a fair way to change things. So you're saying instead of having this code, we just say add first X? Yes, totally fine. That would work as well. That's a nice solution. Because we know that add first works. Now, again, you may not have a full understanding of why did it crash for add last, but it didn't crash for add first. But if you trusted add first. All right. So now that we've got, I mean, we're at the end of a long thrust and a difficult story, but I'm going to tell you like the most brain bending and I think most interesting part of this lecture that is quite unlike how you might have tried to approach it. So this special case is in my heart, it is a Mr. Yuck, right? It doesn't feel right to me. It has a bad code smell, as they say. It's a special case. And what you want to do as a programmer is avoid special cases. You don't want complexity. If you have special cases, they're not simple. With a linear data structure like this, it's only one special case. But if you had some kind of like tree-like data structure, like you might have seen in 61A, having these possible, there might be 4 special cases if you have 2 children, or other types of data structures, it could get very messy. So we do not want special cases. And the way we're going to fix this is we're going to change the structure of our list so that all cases are the same. That's our goal. This is a deep philosophical question, but it's like, how do I do this? Okay, so I want to set up a list so that they're all the same. So the fundamental problem really, like where we started, why we had trouble, is that an empty list has a null first. That's what it says in the constructor, right? If the constructor for no item is called, first is null, okay? And therefore we can't access first.next. That's the problem. And our fix is ugly because there's a special case and we don't want a bunch of special cases. There's just one, but when you do project 1A, if you try and do it this way, you will inflict a lot of pain on yourself because it's just too hard to keep track of. I mean, you can do it, but it's going to involve a lot of like, oh, that didn't work. Let me change it slightly and upload it to the autograder again. Oh, that didn't work. Let me try, like that kind of programming. That's where it leads. So how do we avoid the special case? We want to make all lists, even if they're empty, all the same. So visually, before I write any code, and again, these pictures are what I really want you to understand. So if you drifted for a moment, here's where I bring you in. The list topology that we have so far is as follows. An empty list has a size 0, and then there's and the first was null. But what we're going to change is we're going to have it so there's always a node that's always there, and it's going to have an item in it that we don't care about, and it's just going to be there for sure. Let me go into the code real quick and show you what I mean. So I'm going to say, first of all, I'm going to rename first. I don't like the name first. I'm going to go in and I'm going to say, this is no longer called first, it's called Sentinel. Okay. And what's going to be true is that the Sentinel node is the dummy node front of the list. And the real first item is sentinel.next if it exists. Okay, that's just a note I'm making to myself. So in the empty SList constructor where I have no item, I'm going to say sentinel node equals new int node null. And I don't care what this value is. It just needs to be something. On the slide, I picked the number, I will in a moment pick the number 63. Doesn't matter what it is though. Pick that, okay? And that number is just there in the box because something has to be there. Okay? Likewise, if we create this S list right here, what we'll do is we can do sentinel node equals 12873 again. And then I'll say sentinel.next equals new int node x null. Now, this might seem super weird, like you're just making your life more complicated. But I would argue it's ultimately going to be nicer because all lists always have this node at the front. So we don't need any special cases. With a singly linked list, an S list like this, the benefits are not as clear, but the doubly linked list, which we'll do next time, it's just like way more, just clarion to me. This is the way to do things, okay? So what we're going to do, like the goal is so that when we think about a list that has the numbers 5, 10, and 15, what it should look like, the secret reality that we are creating is that it's going to have a dummy node at the front, a 5, a 10, and a 15. That's going to be what we do, okay? So we're not done yet, though. So all I've done so far is I seemingly have made our lives more annoying by having the sentinel node. And what we need to do next is make all the other methods match. So with add first, when I want to add an item to the front of the list, we need to think carefully, what do we want to do? So the sentinel node equals new int node x sentinel. Does that seem reasonable? Let's see. I have to think about it a little. In fact, that's interesting. Not immediately obvious off the top of my head. I haven't taught class in a couple of years. That's interesting. Okay. So let's look in the visualizer and think about what we want to do. Currently, if we let this code go, if we just add it like so, we have 20 and then 12,873. Does that seem right? No. Okay, not quite right. So what do we want to do instead? Sentinel.next equals new int node. Let's see what happens if we do that. Okay. We're lazy. Okay, we hop that one over. Okay, that looks weird. Sentinel points at this item, and then this thing points back at the sentinel. No, I think what feels right? Sentinel.next, perhaps? Right? Because the idea is we want our list to always be adding items to the very front. Let's add a separate one real quick. We'll double check our thinking. Okay. Okay, L.add first, 10. Okay. So when we step in here, we get to this line of code. Okay, so that's looking good. Okay, then we'll run to the next one around. We add first. We get to this line again. Okay, and we get 10, 20. Okay, everything's in good shape. All right. Git Sentinel. You rename my method. I didn't want you to be named Git Sentinel. Okay, let's call it Git first. All right, if I want to get the first item in the list, what was this note we made to ourselves earlier here? Where's the real first item? Sentinel.next. So we want to say sentinel.next item. Okay. That seems clear to me. The sentinel is not what you want. You want sentinel.next item. And then lastly, we have add last. Here, this code here, if sentinel equals null, does that ever happen? No. Okay, good. Okay, int node p equals sentinel. That seems fine. We advance. Here, nothing seems like it needs to be changed at all. Okay, so int node p equals sentinel. We started the sentinel. We advance p until we get to the last item, and that should be fine. Okay. So let's do L.add last, like 300, L.add last 400. And let's see what list we get after we're done. Let's skip on that one too. So after we've added all these items, we have at the front 12,873. Then we added 20, then 10 in front of 20, then 300, then 400. Everything's looking pretty good. Okay. So what we got out of that is we got to delete the special case. Now it did come, in our case, with a little bit of cognitive cost, which is in the add first method. This was not totally obvious probably to many of you, and it wasn't to me at first, that this is the right thing to do. So the sentinel node, there is some complexity, but ultimately when it comes to more complicated situations, like we'll see in Project 1A, it will definitely be better. Okay, and don't worry, we're gonna have a whole another big chunk of lecture next time where we're gonna think about sentinel nodes some more. We're not quite done. I got 2 more minutes. So what you want to think about is the sentinel node. It is always there for you. It's always there, guaranteed, with its magic number that we don't care about. I rename first to sentinel. Sentinel's never null. We always point at the sentinel node. Its item needs to be some integer. Doesn't matter what we pick. And then we had to fix all the constructors and methods to be compatible with this notion of a sentinel node. So any questions about this before we proceed to my last little philosophical thought? Yeah. Right. So if we were worried about get first crashing, this is really where we would need to start throwing an exception. It's our responsibility. If someone calls get first on an empty list, we have to yell at them. Right. Or we return some dummy value. Yeah. But I think the right way to do is check the size. If the size is 0, tell them you shouldn't be asking for the length or asking for the first. But it depends on how you want to design your list class. Is that yours too? Yeah. Yes.
So, like the central thing kind of like, so I just feel like it's not unintuitive.
It is unintuitive, but it is nice. And it'll be much nicer at the end of the next lecture where it just seems like it's the clear thing to do. With the singly linked list, I admit, it seems like we're going through some pain for not a lot of progress. But the key thing we do is we avoid the special case. All right.
Like the first item, the first one.
This number 63 is irrelevant, right? What we got out of this is this special case doesn't exist. So the very last thing I want to mention is the notion of an invariant. Really what the Sentinel node is about maintaining simple invariants. An invariant is just anything that is guaranteed to be true about your code while it's running, assuming there's no bugs. So an SList with a Sentinel node has at least the following invariants. The first is that the Sentinel reference always points to a Sentinel node. It's never null. The first node, if it exists, is always at sentinel.next. So if you think of the first node is always sentinel.next, if you think about this invariant, this line of code, or this line of text, that's what makes this add first line natural. The front thing is sentinel.next. Instead of being first, it's sentinel.next. So if you just pattern match, it should be there. And lastly, the size variable is always the total number of items that have been added. You can come up with other invariants as well. I have one last thing to say to you guys. Don't worry. Okay. Invariants, they make it easier to reason about your code. You know what needs to be true. And you can think about the goal of your code is to maintain those invariants. All right. That's it. I will see you guys on Friday. Make sure to get working on project 0. Hello, Internet.